Okay guys, we're still in section 4.3. I know there is a ton of stuff already that we've covered with increasing and decreasing and relative extrema. I tried to go back into the homework to see which homework problems you could maybe start and finish by doing the first half of 4.3, but unfortunately most of the problems in the homework have multiple parts and they ask you to do everything in the same problem. But maybe you can start with parts, I don't know, A or B and then save it, but it's up to you. So there's one more big concept that we have to cover in this section called concavity. Okay, and concavity is kind of like if the function curves upward or downward. So here's a couple of different pictures of concave up and a couple of different pictures of concave down. Now I want you to look carefully though at those pictures because we could have concave up but increase. We can also have concave up and decrease. So remember, increase and decrease is what we use our first derivative to determine. And if our first derivative is positive, then we're increasing. If our first derivative is negative, then we're decreasing. But both of these are still concave up. If you look at the concave down pictures, I could have concave down and decrease, but I could also have concave down and increase. And so increasing and decreasing, again, are determined if your first derivative is positive versus negative. Well, concavity is determined if your second derivative is positive or negative. If your second derivative is positive, then your original graph is concave up. If your second derivative is negative, then f is concave down. So again, first derivative tells you increase and decrease, but second derivative helps us tell if it's concave up or concave down. So that's what we're going to discuss in the next few videos. Okay. If you look at these three different graphs change from concave up to concave down or concave down to concave up. That point where it changes from concave up to concave down is what we call a point of inflection. Now, a point of inflection only occurs when it changes concavity, which means the second derivative has to change from positive to negative or negative to positive in order to have a point of inflection there. If it doesn't change, then it is not necessarily a point of inflection. Okay? So just like when we figured out increasing and decreasing, we had to find the derivative. We had to then find our critical numbers. That's where our derivative equaled 0 or didn't exist. And then we had to do our sign chart and test our values. We're going to do the same type of thing for our second derivative. We're going to find the second derivative. We're going to figure out our possible points of inflection. That's where our second derivative equals 0 or does not exist. And then we have to do a sign chart, but with our second derivative. Remember, if our second derivative is positive, then our original function is concave up. If our second derivative is negative, well then our original function is concave down. And if it changes, then that point is called a point of inflection. But it's only a possible point of inflection until there's a sign change. Okay? Let's try example number 4 real quick. Example number 4 says to determine the points of inflection and discuss the concavity. So we know that concavity is really our second derivative. And if there is a change in my second derivative, a sign change in my second derivative, then we have a point of inflection. So let's go ahead and find those two things. Before we can find out concavity, we've got to figure out our second derivative. So pause the video, find your first derivative, find your second derivative, and see if you get the same thing I do. For my first derivative, I got 4x cubed minus 12x squared. For my second derivative, I got 12x squared minus 24x. I hope that you got the same thing. Now that we have our second derivative, we can figure out our possible points of inflection. Remember, these were called critical numbers when we were talking about our first derivative. That's when our second derivative equals 0 or does not exist. So I'm going to set it equal to 0. I'm going to solve. And I get possible points of inflection at 0 and 2. Now I can't call them points of inflection until I do my sign chart. So right now these are only possible points of inflection. So if you look over to the right, this is where I'm going to do my sign chart, but now with my second derivative. So I've got my, let's do red here. So I've got my possible points of inflection on there, my 0 and my 2. And this is where I need to test a number before 0 in my second derivative, a number in between 0 and 2 in my second derivative, and then a number greater than 2 in my second derivative. Remember, I'm worried about my second derivative because that's going to tell me concavity. So, I don't know, plug in a negative 1 to your second derivative. Plug in a positive 1 to your second derivative, and maybe plug in 3 to your second derivative. So using your second derivative equation, plug in those three numbers, and let's see if you get positive or negative in your second derivative. All right, I got positive, I got negative, and then I got positive. But be careful, it doesn't always alternate like that, so make sure that you test each interval. Be careful that you don't miss anything. But I got positive, negative, and positive in my second derivative. If my second derivative is positive, then I know that my original function is concave up. If my second derivative is negative, then I know that my original function is concave down. If my second derivative is positive, I know that I'm concave up. So I should be able to discuss the concavity and also figure out any points of inflection. So we know that the original function, f, is concave up from negative infinity to 0, and then again from 2 to infinity. We know that because the second derivative is positive. So if I ask you to justify your answer, you should be able to give me that notation. We also know that f is concave down from 0 to 2. Justifying your answer, well, we know it's concave down there because the second derivative is negative. Remember, points of inflection are found anytime that my second derivative has a sign change. So it looks like I have a point of inflection here at 0, also at x equals 2. But those are points of inflection. That means I need an x and a y. So if x is 0 and x is 2, then how do you think we're going to find the y value for our point of inflection? Well, remember, we're looking for points in my original graph that change concavity. So you should be plugging that 0 into your original f of x. You should be plugging in the 2 to your original f of x, so you can actually find the points of inflection in your original graph. I ended up getting points of inflection at 0, 0 and 2, negative 16. I hope that you got the same thing that I did. So first derivative, remember, is increasing or decreasing. Second derivative is concavity. Let's do a few more practices in the next video.